Hi, my name is Anna Brieland-Shoultz, and this summer I researched cavitation and converging diverging nozzles. I had the pleasure of working with Professor Eric Johnsen of the Mechanical Engineering Department here at the University of Michigan and the members of his computational flow physics lab. My project revolved around investigating cavitation phenomena in converging diverging nozzles. For those of you who don't know, a liquid undergoes cavitation when the ambient pressure of the liquid falls beneath the vapor pressure of that liquid. When this happens, small voids in the liquid expand to form vapor or gas bubbles, which collapse and rebound as the ambient pressure changes. Cavitation occurs in many physical situations. Collapsing bubbles form shock waves, which can negatively impact mechanical devices like fuel injector nozzles or ship propellers. These shock waves can also be used for good, however. For example, in shockwave lithotripsy, shock waves formed by collapsing bubbles are used to break kidney stones into pieces small enough to be processed by the human body. The goal of my project was to mathematically model cavitation in converging diverging nozzles. In a CD nozzle, regions of relatively high pressure flank a lower pressure region at the nozzle throat. Cavitation bubbles form in this low pressure region. As the bubbles continue to move through the nozzle, they collapse and rebound due to the increase in pressure. This causes shock waves to form. So I wrote a MATLAB program which takes many different pressure inputs and returns a plot of bubble radius versus time. So this slide shows one example of what my program can do. The top curve is a pressure versus time curve, which is similar to what would be produced for a symmetric converging diverging nozzle. The second curve is a plot of radius versus time for a compressible flow, and the third is radius versus time for incompressible flow. You can see that the compressible flow oscillates significantly less than the incompressible due to damping. Both of these curves evidence viscosity and surface tension effects also. So this project could have been expanded into a couple of different directions. We could further investigate cavitation in diesel fuel injectors by updating the mathematical model to include the fuel injector specifications. We could study interactions of multiple bubbles because my example only took one bubble into account. And the formation of shock waves could also be mathematically modeled. Thank you for listening.